Alright guys, so now we're going to look at how we would calculate the molar heat of combustion from experimental data. How we would calculate that. We'll take special care to point out which parts are going to be your experimental data as we go. Alright, so essentially, this is how the experiment will work. First off, you've got this bad boy here. This is your experimental setup. This is the calorimeter, which can be a copper container, an aluminium can. That's the one we'll probably use in the experiments. And it's all fine. The aluminium can works quite well. So, what you're measuring, you're going to measure the change in the temperature of water. Okay, this is the fuel from your spirit burner. This is the fuel you're burning to heat this up. Okay, so what is the molar heat of combustion? It is the heat liberated when 1 mole of a compound combusts completely with oxygen at a constant temperature. Combust completely. Complete combustion is really, really important. So there's several steps. The first thing you do is you work out what the enthalpy change is. Okay, so what's your enthalpy for the reaction? And that's this here. Now you do that by measuring the change in temperature. It's a formula you might be familiar with. You then work out the moles of fuel burned. You use a second formula for that, which you should most definitely be familiar with by now. And you then divide the fuel, so the enthalpy change, by the moles of fuel. And it looks like this. So there's two ways of writing this. You can write it as delta CH or delta H comb, which is short for combustion. And it is the enthalpy divided by the moles. Pretty simple. And there it is up there. So let's have a look at how you would work this out. So essentially, your reaction will kind of look like this, except it's a little bit different. We'll put a bracket around there. Now, sometimes you'll just have the information for the water. They'll ignore whatever the calorimeter is. Sometimes, but not always. So if they're not ignoring what the calorimeter is, you need to make this one here for water, and that one there for water, which you can't expect it to know that one. Then you have to add in the enthalpy for the container, which is the mass of the container times by the specific heat capacity of the container, which might be aluminium or copper, times by the delta T, so change in temperature, that you record here. So that's still this temperature here that you're recording. Alright, so that's your formula there. Now, sometimes, as I said, if there is no container given in the data, then you just use this one. If we have the information about the container, we have to do this one, and that will get us a more accurate result. So, what have we got? Delta H is the enthalpy change in joules. It's important. You're probably going to convert that to kilojoules, which just means divide by 1,000. M is your mass of water, or mass of that or that. Thermal capacity is for whatever it is you're measuring, whether it's the water or the container. And delta T is the change in temperature that you're measuring with a thermometer. That is the experimental data you're collecting, is the change in temperature. These ones here are all things that you will look up. Well, you don't look at, that's what you're looking at. You'll look these up and work it out. Okay, so the mass of fuel is simple again. It's basically initial minus the final masses. That's your experimental data. So then you use N equals M over molar mass, so mass over molar mass, to work out the moles of fuel. You need to work out the moles of fuel. And that's it. Alright, so there's a video after this. There's another video with this, a companion video, which will be a worked experimental, a worked question, so a worked example. Alright, see you then.